Welcome back, Physics A, to circular motion. As we come into day 2 and start working on some practice problems, I wanted to review where we got in the slideshow yesterday. So looking at this animation, we have our mass moving in a uniform circular motion at constant speed. And in order for that to happen, we discussed yesterday, using some vector analysis, that the change in velocity, and therefore the acceleration, must be directed toward the center of the circle. So our vector analysis is going to be that the velocity is tangent to the circle, represented by these red arrows, and your acceleration is always directed towards the center of the circle, which is summarized by this term centripetal, which means towards the center. So A sub c is going to be centripetal acceleration toward the center of the circle. It can be calculated by v squared over r, where v is our magnitude of the speed, because the direction of the velocity vector is always changing. So v is going to represent the magnitude of our speed. And we can calculate the magnitude of that speed, as we mentioned in our notes, that speed is distance over time. So looking at that distance around the circle, is your circumference 2 pi r, and the time around the circle is your period, the time of one cycle. So your speed can be calculated by your circumference over your period, 2 pi r over t. All right. And then we have our calculations here for centripetal acceleration. And here is the 6 problems that we'll look at today. I will walk you through problem 1 as an example, and then your homework is to work on 2, 3, 4, 5, and 6 to discuss at the beginning of our next class. All right, so please make sure you show your work on a separate piece of paper, following along with the steps that I'm about to do here for question number 1. So question number 1 involves an audio CD, a compact disc, that are now fading out of use. But most CDs and DVDs have a diameter of 120 millimeters. All right, so we're going to have to take that 120 millimeters, or 12 centimeters, and convert this to meters. All right, unit conversion is always something that we have to take into account. And they spin at a maximum rate of 540 revolutions per minute, or RPMs. So we're going to look at that constant rate of 540 RPMs. So a couple things that we have to note just from the start. We have to convert our units for the diameter so that it's in meters. And we also have to convert our 540 revolutions per minute to seconds so that it's in our proper SI units. And in order to do this, we take our 540 revolutions per minute, and we want to convert this to seconds. So that's going to involve canceling out minutes and converting to seconds. And we know that 1 minute contains 60 seconds. So we're going to wind up with then revolutions per second. Dividing 540 by 60 becomes 9. 540 divided by 60 is 9. And our units, minutes cancels, and we wind up with revolutions per second. So 9 revolutions per second, which revolutions doesn't really have a unit. So this really is 9 1/seconds. And that unit of 1/seconds we call hertz. Nine hertz. And hertz is going to be our unit for the quantity of frequency. All right, so this is going to be our frequency, which is measured in 1/seconds, or hertz. And we can think of this as how many cycles per 1 second. How many cycles happen in 1 second? Whereas the period is how many seconds does it take to complete 1 cycle. Your frequency is the reciprocal of that. How many cycles happen in 1 second? So your period is the reciprocal of your frequency, and therefore your frequency is the reciprocal of your period. So 2 more equations, expressions there to relate your period and your frequency. Some space there. As we go through our calculations. So really analyzing your units. Am I searching for how much time is required for 1 revolution? Or am I calculating how many revolutions happen in 1 second? What is my frequency? So cycles per second or revolutions per minute can also be a unit for your frequency. So this leads into our first question for problem A. 1A is asking how much time is required for 1 revolution. So the time for 1 revolution is going to be my period. Right? The time of 1 revolution is my period. So my period, we just clarified, can be calculated by the reciprocal of the frequency. And I've simplified my frequency of 540 RPMs, dividing by 60 seconds per minute, to be 9 hertz. My period then is 1 over 9 hertz, which is 1 over seconds. So 1 over seconds is going to wind up with units of seconds. 1 over 9 is 0.111 seconds. And since we had 2 sig figs given in the problem, I should give my answer to 2 sig figs of just 0.11. Alright, so as you go through your homework problems, you'll get some experience working with frequency and period. Recognizing period is the time of 1 cycle, and frequency is how many cycles happen in 1 second. Alright, 1B is saying if there is a speck of dust riding on the outside edge of the CD, what is its tangential speed? So it's asking for my tangential speed here, 2 pi r over t. We just solved for our period t, which is wonderful. I guess you could also substitute 2 pi r times your frequency, right? Since 1 over t is your frequency. So you could multiply by 9 or you could divide by 0.11. It's going to be the same math. But in either case, we need to solve for our radius. Right? We need to solve for our radius. They gave us a diameter of 120 millimeters. And I know that my radius is going to be half of that. My radius equals half of my diameter. So that's going to be 60 millimeters. But, as I mentioned earlier, you need to convert this to meters. So, converting 2 meters from millimeters, recognizing that 1 meter has 1,000 millimeters. So you'll be dividing by 1,000. So 60 divided by 1,000 is 0.060 meters. Scooching that decimal place 3 places to the left. And that can then be plugged into your calculations for speed. so that my speed is 2 pi r divided by my period. And as I said earlier, you could divide by 0.11 for your period, or you can multiply by 9 for your frequency. You'll wind up with the same math. Which, plugging this in really quick, two pi r is 0.3768 divided by my period of 0.11 seconds gets me a speed of 3.4254 meters per second. So again, giving my answer to 2 sig figs, I get a speed of 3.4 meters per second. And finishing out our example problem of 1c, what centripetal acceleration does the speck of dust experience? Centripetal acceleration is v squared over r, so I get to plug in my speed of 3.425. I don't want to round too early, and get an acceleration that's incorrect because it's rounded too much, divided by our radius of, we saw for this above in red, 0.060 meters. Alright, so 3.425 squared is 11.73 divided by 0.060, and I get a centripetal acceleration of 195.5 meters per second squared. It's still the same units, it's still normal acceleration, but rounded to 2 sig figs, that gets a little funky. It's going to be 200, and there's my second sig fig with the bar. Meters per second squared toward the center. Because my centripetal acceleration, because it's centripetal, is always towards the center. Alright, so there's our example for question 1. Converting our diameter to the radius in proper units of meters, taking our frequency to find period, taking the reciprocal of the frequency to find our period, and then using our equations for average speed and centripetal acceleration to solve for those values. Use this example as a framework to complete questions 2, 3, 4, 5, and 6. Best of luck, and we'll go over the solutions or any questions you may have during our next class.